We'll now talk about and derive the fundamental equation that's used to mathematically describe perspective. What I'm showing here is I have two parallel lines in blue. And say the black here represents an object that we're viewing in the distance. Its height is going to remain constant at S because S represents the actual height of the object. And as the object moves out into the distance or comes closer to us, the height of the object, the actual size of the object, does not change. It remains constant. It's just our perception of the size of the object that changes, but the actual size of the object remains fixed, say at a height S. Now, remember the relationship between subtended arc length and the angle that subtends that arc length is S equals R theta, where R is the distance from the vertex of the angle out to the arc length that's being subtended. Remember, we have this relationship. If we have the vertex and some angle theta and we go out a distance R, then the size of the arc that's subtended is S. And this is a relationship between the three parameters. We have the angle theta, the angular measure that we cite the top and the bottom of the arc or the object, and the distance out, and this is the relationship. And as long as the angle is small, the actual arc compared to the straight line distance is very, very tiny and insignificant. And I'll derive that in a later module where we can actually calculate how much that error is. But if the angle theta is less than 10 degrees, the difference between, say, where you're sweeping out an actual arc to the straight line distance, what you have, if you look at it closely, let's look at it. If I sweep out an angle, I see an arc, but I can approximate it with a straight line where we have a triangle here, an actual triangle with a straight line. And this distance, the total arc length distance compared to the straight line distance, called D, are essentially the same for angles less than 10 degrees. The difference is really quite insignificant. We'll derive that later, but we'll just take my word for it right now. Okay, so here we have the object in the near field and the far field. This S is the actual size of the object. Now, when it's out in the distance, we as an observer are going to sight the top and the bottom of the object, and we're going to see the angular measure as being theta F. Well, the distance out to that object, we'll call it RF. So the relationship then is S is equal to theta F times RF from our equation here that we derived earlier. Now, when we look at the object, when it's up closer to us, we can see that its angular size is actually bigger. It appears bigger to us as it gets nearer to us. And that makes sense. We've observed that in our daily lives. So if we're going to look at this object, we're going to sight the top and the bottom of the object, and we can see that the angular size is indeed bigger than the angular size in the distance. So we'll call this theta n for the angular size when the object is near to us. And we can see from the diagram that the angular size when the object is near us is greater than the angular size when it's off in the distance. This angle theta n is bigger than theta f. Well, we can show that mathematically. When the object is near us, the distance, we'll call this r near. And we can see from here that the distance, viewing the object in the distance, that distance is greater than the near distance. RF is greater than RN. I mean, that's common sense here. The RF means the object is way out in the distance. RN is a distance when it's up close near us. Now, the size of the object doesn't change, so S remains constant. So in the near field, our relationship then is S is equal to theta n times Rn. So we can equate these, that theta f Rf is equal to S, which is equal to theta n Rn. So we have a relationship. We can solve, say, for theta n in terms of theta f. So theta n then will be equal to theta f Rf over Rn. I'm just dividing through both sides by Rn. Well, Rf is greater than Rn, so if we divide through by Rn, we have Rf over Rn is greater than 1. Well, this quantity then is greater than 1, so it multiplies theta f, so theta f times a number greater than 1 is going to be greater than theta f. So we can see then from this that theta n is indeed greater than theta f. This theta f times a number greater than 1 is greater than theta f. So Rn is greater than theta f, as we can plainly see from the diagram. So this is the fundamental equation for perspective that we'll be using later on. Very important equation, and it relates perceived size of an object as a function of the distance from viewing. Now, I'm going to talk a little bit about some celestial mechanics and viewing total eclipses. Right now, currently, we enjoy total solar eclipses, but that's not always going to be true. The moon is receding away from the Earth at a rate of about 3.78 centimeters per year. So you can imagine that right now the moon's disk covers the sun's disk totally. So the light of the sun gets blocked out. Well, as the moon moves away from the Earth, its perceived disk size is going to get smaller and smaller to the point of where it's no longer going to be able to cover the sun's disk. And then there will no longer be total solar eclipses. Well, knowing the rate at which the moon is receding from the Earth and the distance that the moon is from the Earth, the size of the moon, the size of the sun, the distance the Earth is from the sun, we can calculate at what point in the life of the moon-Earth system that the moon will no longer be able to cover the sun. So we'll look at that now. Here I have a diagram, of course it's not to scale, that represents the Earth, Moon, Sun system. We have an observer on the surface of the Earth, standing right here, observing a total eclipse. That occurs when the moon gets between the sun and the Earth. It turns out that the distance to the sun and the sun's diameter is about in the same ratio as the moon diameter is with its distance from the Earth. The ratio of the diameter to the distance is the same for the sun and the moon. That's why the moon totally blocks out the sun at about having the same angular disk size. Now here are the important parameters. We have the moon diameter, 3474.2 kilometers. The radius of the Earth is 6371 kilometers. The diameter of the Sun is 1,391,400 kilometers. Now we have for the moon the apogee and perigee. The moon's orbit about the Earth and the Earth's orbit about the Sun are not perfect circles. They're ellipses. It's a little bit of a squash circle that gives it an elliptical orbit, but it's pretty close to being a perfect circle. But there are discrepancies. For the moon, the furthest distance that the moon is away from the Earth is called the apogee. The closest approach is called the perigee. So if we have the Earth sitting here and the moon orbiting, this is greatly exaggerated. The moon's orbit is almost perfectly circular. But the furthest distance out when the moon is out here is called the apogee, and that's at 406,700 kilometers. And at its closest approach to the Earth, called the perigee, is at 356,500 kilometers. We will call the distance, the furthest distance that the moon is from the Earth, RM. That's the furthest distance, that's its perigee. Now, for the Earth and the Sun, the same thing happens, except now we have the Sun located at the foci of an ellipse. I've talked about this in another video where I've discussed ellipses. You're always guaranteed that the central body is at the focus of an ellipse. So here we have the Earth orbiting. The furthest distance the Earth is from the Sun is called the aphelion, and that's 152.1 million kilometers. And the closest approach the Earth has to the Sun is called the perihelion at 147,000.1 million kilometers. And the semi-major axis distance is called an astronomical unit, and it is set at this value, 149,597,870 million 0.7 kilometers. And the eccentricity, which is a figure of merit of basically the squashiness of the orbit, if it was perfectly circular, the eccentricity would be 0, and you can see it's a very small value, so it's very close to 0. Eccentricities for ellipses vary between 1 and 0. If the eccentricity is 0, you have a circular orbit, and if the eccentricity is 1, it collapses and you get a straight line, which is called a degenerate ellipse. Now, we will call the distance. Now, these distances that are given in kilometers for the distance between the moon and the Earth and the Sun are center-to-center distances. That is, the distance from the Earth to the Sun goes from the center of the Sun to the center of the Earth, and we call that RS. That's this number here, the aphelion. And the distance from the center of the moon to the center of the Earth is RM, standing for moon, and we'll choose that to be the perigee. And the reason why I'm doing that is this is the worst case. Think about it for a moment. The moon will appear to have its largest disk size when it is at the closest approach to the Earth, and it will cover the Sun in the maximum that it can when the Sun is furthest away. So when the moon is closest to the Earth and the Earth is furthest from the Sun is when the maximum size of the lunar disk can cover the disk of the Sun. Now, let's calculate out what those numbers are. Now, what we have to do, what we're going to do here is, using our formula, remember that the arc length subtended is the distance out times theta, where r is the distance from the observer. Well, the observer is at the surface of the Earth, so we have to subtract off the radius of the Earth because rm and rs are center-to-center distances. So what we have then is the distance from the observer on the surface of the Earth to the moon will be rm minus re, and the distance from the observer on the surface of the Earth to the sun will be rs minus re. Right, well, let's look at these numbers. We'll call r1 is rm minus re. Well, rm minus re is 356,500,000 kilometers, and we're going to subtract off the radius of the Earth, which is 6371 kilometers. And this number, performing that subtraction, we get 350,129 kilometers. R2, let's call that the distance to the sun, center distance, minus the radius of the Earth. Well, distance to the sun in the aphelion, where it's furthest away, is 152.1 million kilometers. So that's 10 times 10 to the 6. And we subtract off the radius of the Earth, which is, expressing it in terms of millions of kilometers, it would be 0.0 let's see, 6371. We go 1, 2, 3. That's kilometers. This is kilometers. So we move 6 decimal places. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So that's in terms of kilometers. So we subtract 0.006371 from 152.1, and this is also times 10 to the 6. So that comes out to 152.094 times 10 to the 6 kilometers. So the radius of the Earth, subtracting off the radius of the Earth doesn't affect that number much, but it does affect the moon distance. Now, let's calculate what is the angle, the angular measure that we're going to measure, we're going to see the moon at. We'll call this theta m. Well, solving for theta m, that's just s over r. Well, S is the diameter of the moon, and R is our R1. That's this value here, from the surface of the Earth to the center of the moon. So we'll call that R1. Well, these numbers, putting in, the diameter of the moon is 3474 kilometers. We have the diameter of the moon, and we divide by R1, which is 350,129 kilometers. Well, this number, if you perform the division, comes out to 0.009922 radians. Remember, the angular measure in this equation is theta is in radians, not degrees. It comes out in radians when you perform that division. Well, this in terms of degrees, remember if we multiply this by 180 and divide by pi, we convert radians to degrees. So 0.009922, this is radians. We divide by pi radians and multiply by 180 degrees. So this comes out to 0.568 degrees. If we multiply by 60, we can get how many minutes this is. And this works out to 34.11 minutes in angular measure. Now, let's look at the angular measure of what we see the sun's disk to be. Well, again, it's the diameter. In this case, we use the diameter of the sun divided by the distance from the surface of the earth to the sun. Well, the diameter of the sun is 1,391,400 kilometers, and we divide by the distance, which is R2, which is 152.094 times 10 to the 6 kilometers. So, working this out, this is 1.39 times 10 to the 6, so this is 1.391 divided by 152.09. Well, that comes out to 0.009148 radians. Very close to the angular dimension of the moon's disk. And if we multiply this number by 180 and divide by pi, we get degrees. So this becomes 0.524 degrees. And multiply by 60 to get minutes. So this is 31.45 minutes. That's why the moon and the sun appear to be the same size in the sky. From our perspective, given their actual sizes and the distances that they are away from the Earth's surface, they appear to be the same size. The mathematics shows us that to be true. They only differ in size, in this case, by less than 3 minutes of an angle. Now, we can also see in this case that when the sun is furthest away from the Earth and the moon has its closest approach, that the size of the moon's disk is a little bit bigger than the sun. So it does cover the sun completely. The angular measure of the moon is greater than the angular size of the sun. So it totally covers the sun. Now, what will happen, say, as the moon is receding away from the Earth? As the moon recedes away from the Earth, what do we get? The moon is going to move out here. Remember, its size remains the same, and we can see that it's no longer going to cover the sun's disk as it moves away. It's the perceived size, angular size of the moon gets smaller and smaller, and it will get so small that it will no longer cover the sun. Let's figure out at what point that is going to occur. Well, the way we do that is we need to assume, or not assume, but what we're going to do is we want to find how far away the moon needs to be from the Earth so that its angular size just covers, or is just exactly the same size as the sun. See, right now it's a little bit bigger than the sun. So what we're going to do is choose the angular size of the moon to equal that of the sun, and then compute the distance that the moon needs to be away from the Earth to give us that angular size. So we'll do that here. So, in using our equation, S equals R theta, remember theta has to be in radians. So we have to choose for the angular size of the moon to be that of the sun in radians. So that's the number we're going to choose. So the angular size, we know that the size of the moon, remember S is the diameter of the moon, putting in terms of our variables here. The arc length is the diameter of the moon, and that's going to equal R1, the distance from the surface of the Earth to the moon center, and times theta. Well, theta in this case, we're going to make it equal to the same size of the sun. So solving the distance R1 will just be equal to the diameter of the moon divided by the angular size of the sun. Well, the diameter of the moon is 3474 kilometers, and we divide by the angular size of the sun, which is 0.009148 radians. Well, performing that division, this comes out to 379,755 kilometers. Okay. At that distance, R1, when the moon gets out that distance from the Earth's surface, it will exactly cover the sun, and any further distance that it moves, it will no longer be able to cover the disk of the sun. So you'll no longer get a total solar eclipse. Now, we started off with a distance of R1 to the moon of that. So let's see how much further it needs to recede for that to occur. So we're going to subtract off 350,129 kilometers from this. And subtracting that number, we get 29,626 kilometers. So if the moon moves out further by 29,626 kilometers, it will no longer be able to cover the disk of the sun. Well, when will that occur? We know that the moon is moving away from the Earth at a rate of 3.78 centimeters per year. Or let's put it in terms of meters. So this, moving 2 decimal places to the left, it's 0.0378 meters per year. And it needs to move a distance, this is the rate, its velocity receding from the Earth. So distance divided by velocity will give us time. So 29,626 kilometers is 29,626,000 million meters. And we divide that by 0.378 meters per year. So this gives us how many years from now this will occur. If we perform this division, we get 783.8 times 10 to the 6 years, or this tells us roughly 784 million years from now, we will lose our ability to see total eclipses of the sun. So that wraps it up on this particular module. And the next one we'll start talking about trigonometry.